Beneath the rust-colored sands of Mars lies a resource that could rewrite humanity's future. This is not about finding a puddle. It is about unlocking a buried treasure of subsurface ice with the power to fuel and protect an entire civilization. By the end of this, you will understand exactly how this frozen water could be the key to turning a desolate planet into a second home for humanity. We will uncover how we find this hidden ice, the machines that will dig it up, and the incredible ways it can be transformed into breathable air, rocket fuel, and a shield against cosmic dangers. How do you picture our species making its first permanent mark on another world? The surface of Mars presents a face of profound desolation, a seemingly endless desert of red dust and rock. Yet this dry exterior is a mask hiding a world with a deep and water-rich history. Evidence gathered over decades tells a new story, one where rivers once carved canyons and vast oceans may have pooled. The clearest sign of this past is not on the surface, but just beneath it. Orbiting spacecraft have mapped the planet in incredible detail, revealing what our eyes cannot see. Instruments like the SHARAD radar on NASA's Mars Reconnaissance orbiter send signals deep into the ground, painting a picture of the subsurface. Their findings are astonishing. They show vast reservoirs of water ice, not just at the frozen poles but buried across the planet's middle latitudes. This is not always a clean, clear sheet of ice. Often, it exists as what scientists call a dirty ice mixture, where frozen water is locked in a matrix of Martian soil and rock. In other places, it forms layers of relatively pure ice, a buried treasure chest waiting to be opened. The mid-latitude regions are particularly promising. Here, the ice remains stable, protected from sublimating directly into the thin atmosphere, yet it is not trapped in the permanent, deep freeze of the polar caps. This makes these areas the most logical and practical places for humanity to establish its first footholds. Knowing exactly where this ice is hidden and in what form is the critical first chapter in the story of living on Mars. It is the map that will guide the first great dig. Mapping these buried reservoirs from orbit gives us the treasure map, but we still need to send in the ground crew to dig the first test hole. The first major hurdle is pinpointing the exact location and depth of the most accessible ice deposits. Orbital instruments are incredibly powerful, detecting the faint hydrogen signature that hints at water below, but they cannot tell us everything. They cannot confirm the ice's purity, its exact consistency, or how hard it will be to dig up. This is where the scout mission comes in. Picture a single, autonomous rover, smaller than the ones we have seen before, designed for one primary purpose, to be a prospector. It would travel to a promising site identified from space, a place where the radar suggests ice is tantalizingly close to the surface. Its most important tool is not a camera, but a drill. This robotic arm would extend and begin to bite into the red soil, coring down just a meter or two to retrieve a sample of what lies beneath. That moment of truth, when the sample is analyzed in the rover's onboard lab, would confirm the presence of water ice and measure its quality. Is it the relatively pure ice we hope for, or a rock-hard mixture of dirt and ice that will be more challenging to process? Drilling on Mars is an engineering puzzle all its own. The planet's low gravity offers less traction, making it harder to push a drill bit down with force. Temperatures swing to extremes that can make metal brittle and seals fail. And the ice itself is not like the soft snow in your freezer. In the perpetual deep cold of the Martian subsurface, water ice can have the consistency and hardness of concrete. A scout rover must be built to withstand these brutal conditions, its systems robust enough to operate far from any human help. This phase of reconnaissance and verification is a quiet, methodical, and absolutely essential prelude to the grander operations that will follow. It is the difference between guessing where to build a well and knowing with certainty that you are standing right on top of the aquifer. Once the Prospector rover confirms a rich deposit, the real work begins. The challenge shifts from finding the ice to physically pulling it from the ground, a monumental task of engineering on a world that offers no help. Mars provides no air to breathe, no liquid water to use, and no fuel depot to refill the tanks. Every piece of equipment, every watt of power must be brought from Earth or generated on site, making efficiency the highest law. One of the most promising methods for extraction is a technique that sounds like science fiction but is grounded in terrestrial technology. Imagine a heated drill probe, a device that sinks into the Martian soil and uses its own thermal energy to melt the surrounding ice. It would not dig or excavate in the traditional sense. Instead, it would create a small, liquid water bubble deep underground, which could then be pumped directly to the surface. This is similar to geothermal drilling on Earth, where we tap into heat beneath our feet, but here the heat source is artificial and its target is frozen solid. This method is beautifully efficient because it minimizes moving parts and avoids the immense difficulty of hauling heavy, frozen soil to the surface. The water arrives ready for the next stage, already in a liquid state. The alternative is more direct and more physically demanding. Large, autonomous excavation rovers would operate like miniature, robotic strip mines. Their massive buckets and drills would bite into the frozen ground, breaking up the icy soil and transporting it to a central processing plant. Think of it like mining for coal or minerals on Earth, but in an environment with 1/3 the gravity, virtually no atmosphere, and a communication delay with mission control that makes real-time guidance impossible. These machines would need to be incredibly robust and smart, capable of working for months without a single command from Earth, navigating the treacherous, rocky terrain and managing their own power and maintenance. The energy required for either method is staggering. Melting ice or digging through frozen ground are power-hungry activities. This is why any future ice mining operation will be inextricably linked to a massive solar array or even a small nuclear reactor, a dedicated power plant whose sole purpose is to fuel the creation of the colony's most precious resource. Successfully pulling that first bucket of icy soil or pumping that first liter of water to the surface is the critical gateway. In that moment, subsurface ice ceases to be a geological feature on a map. It transforms into a tangible, life-giving asset, the very blood of a new civilization waiting to be processed and put to work. That first liter of water pumped to the surface is more than a scientific sample. It is the seed of a biosphere. Once extracted, this water begins a remarkable transformation, starting with its most fundamental role, keeping human beings alive. After being melted and rigorously purified to remove any Martian soil or potential contaminants, it becomes the absolute cornerstone of a closed-loop life support system. This means the water is used, cleaned, and reused again and again in a cycle that mimics the natural processes of Earth. It provides drinking water for the crew and is essential for basic hygiene, helping to maintain a healthy environment inside the pressurized habitats. But its most revolutionary use is in the Colonies farm. Picture a brightly lit module, filled not with soil but with rows of green plants, their roots misted with a nutrient-rich water solution or suspended directly in it. This is hydroponics and aeroponics, and the solvent for all those essential nutrients is the water mined from the ground below. growing food locally like this is a monumental shift. It drastically cuts the colony's dependence on the exorbitantly expensive and logistically daunting shipments of food from Earth, a concept known as in situ resource utilization, or simply living off the land. This ability to create a self-sustaining, regenerative biosphere is the first and most important pillar of a permanent colony. It turns a remote outpost into a true home, all starting from that reliable supply of water, which then unlocks even more advanced and powerful applications, like generating energy itself. But the true revolution begins when you pass an electrical current through that purified water. This simple process, known as electrolysis, is the key that unlocks the stored energy within. The electric charge forces the water molecules to split apart, separating into their two fundamental components, hydrogen gas and oxygen gas. On Earth, this is a common laboratory demonstration. On Mars, it becomes the colony's lifeline and its launch pad. The oxygen is immediately useful, pumped directly into the habitat's atmosphere to replenish the air that astronauts breathe. It closes another critical loop in the life support system, creating breathable air from a resource dug out of the ground. Yet the oxygen is only half of the story. The other product, hydrogen, is just as vital. To become fuel, both of these gases undergo a dramatic transformation. They are cooled to incredibly low temperatures, condensing into pale, super-cold liquids. Liquefied hydrogen and oxygen are the very same propellants that powered the space shuttle's main engines. Stored in heavily insulated tanks, they become the energetic heart of a Martian fuel depot. This changes the entire economics of space travel. A spacecraft launching from Earth for Mars would no longer need to carry the immense weight of the fuel required for its return trip. It could arrive with nearly empty tanks, knowing it will refuel on the Martian surface using locally sourced water. This single innovation slashes the cost and complexity of a mission by an almost unimaginable degree, turning a one-way trip into a round-trip itinerary. The water ice, once transformed, becomes more than just a resource for survival. It becomes the very thing that enables the colony to reach out, to grow, and to connect back to Earth. And this principle of transformation extends even further, creating a power source that could sustain the colony for generations. The very same hydrogen and oxygen destined for rocket engines hold another secret, a way to keep the lights on long after the sun has set. This is the magic of the fuel cell, a device that performs electrolysis in reverse. Inside a fuel cell, hydrogen and oxygen are combined in a controlled chemical reaction. This process does not involve burning, there are no flames. Instead, it directly generates a steady, silent flow of electricity. Its only emission is a trickle of perfectly pure, distilled water, which can be fed right back into the colony's life support system. It is a beautifully closed loop, a cycle of creation that powers a world. This simple principle solves one of the greatest challenges of living on Mars, the unreliable sun. Solar power is abundant during the day, but a Martian night lasts for over 12 hours, and global dust storms can blot out the sun for weeks, even months. A colony cannot simply power down and wait for the storm to pass. Life support, communication systems, and scientific experiments demand a constant, unwavering supply of energy. This is where water becomes the colony's energy bank. Imagine a daily cycle powered by the sun. During the daylight hours, massive solar arrays generate more electricity than the colony immediately needs. Instead of letting this surplus energy go to waste, it is diverted to the electrolyzers, which work tirelessly to split water into hydrogen and oxygen gas. This is the act of storing energy, transforming electrical power into chemical potential locked inside these two gases. Then, as the sun dips below the horizon, the fuel cells quietly take over. They draw from the stored hydrogen and oxygen, combining them to generate electricity throughout the long, cold night. When a dust storm darkens the sky, the fuel cells become the colony's primary power plant, ensuring that the habitats remain warm, the air stays breathable, and the lights never flicker. This creates a resilient and reliable energy grid, built not on a single source but on a flexible, interchangeable system. The water mined from the ground becomes the universal currency for energy, a resource that can be transformed at will into breathable air, rocket fuel, or the electricity that powers everything from habitat, lights to manufacturing facilities that build the colony's future. The discovery of subsurface ice was the finding of a resource, but its true power is in this incredible versatility. Yet, the value of this buried ice extends far beyond the machinery it fuels, offering a profound and personal layer of protection for the people who will call this harsh world home. But this versatile resource offers an even more personal form of protection. The same Martian environment that provides water also presents one of the most severe hazards to human life, a constant, invisible rain of radiation. Unlike Earth, Mars has lost its global magnetic field and possesses only a wisp of an atmosphere. This leaves the surface exposed to the full intensity of galactic cosmic rays from deep space and sudden, intense bursts of solar particles from our own sun. An astronaut on the surface would be subject to a radiation dose hundreds of times higher than what we experience on Earth, a long-term health risk that no simple spacesuit can block. This is where the ice transforms from a resource into a refuge. Water, specifically the hydrogen atoms within it, is remarkably effective at absorbing and scattering these high-energy particles. It is a principle we see in the protective water tanks surrounding nuclear reactors on Earth. On Mars, this natural property can be woven directly into the architecture of survival. Imagine a habitat not built on the surface but within it. Excavation machines could carve out large, underground caverns, using the native rock as a primary shield. Then the walls are lined with thick blocks of clear ice, harvested from the ground just outside the door. This creates a layered defense, a bunker that is both strong and strangely beautiful. Another design envisions surface habitats crowned with a vaulted ceiling made of ice, a glowing, translucent dome that filters the harsh sunlight while deflecting harmful radiation. It is the modern equivalent of an igloo, a structure that uses the local material to provide safety from the elements. Only these elements are subatomic and far more dangerous. The colonists living inside would look up through walls of ice, seeing the distorted Martian sky, while knowing that this very substance is what allows them to live there safely. The ice, once a symbol of a cold and dead world, becomes the very barrier that makes life possible, turning a planetary threat into the primary building material for a new home. These translucent walls of ice offer more than just protection. They can become the very architecture of a new world. The same frozen water that shields colonists from radiation can be shaped into the structures they live and work in, transforming a raw resource into a built environment. This is not science fiction. It is a practical engineering pathway known as in situ resource utilization pushed to its logical extreme. The most immediate application is for greenhouses. A dome or wall constructed from clear ice panels would act as a naturally insulated window, allowing the full spectrum of sunlight to reach the plants inside while maintaining a stable, warm temperature. The ice itself is a superb insulator, preventing the bitter cold of the Martian exterior from leaching away the precious heat generated within the growing module. This creates a self-regulating environment where the primary building material actively contributes to the system's success. But how do you build with something as seemingly fragile as ice? The answer lies in treating it not like the ice in your freezer, but as a sophisticated composite material. Pure water ice is brittle, but when mixed with a small percentage of Martian soil or regolith, it creates a substance with much greater structural integrity. Think of it as a form of frozen concrete where the soil acts as an aggregate, giving the ice strength and resistance to cracking. Advanced construction techniques could take this even further. One concept involves large-scale 3D printing. A robotic printer would move across the construction site, layering down a mixture of water and regolith in precise patterns, building up walls layer by layer in the freezing Martian air. The water would flash freeze almost instantly, locking the structure into place. For clear panels, printers could use purer water, creating transparent slabs that are thick enough to be strong but still allow light to pass through. This approach solves one of the biggest logistical nightmares of interplanetary colonization: the staggering cost of shipping building materials from Earth. Every brick, every steel beam, and every sheet of glass launched from our planet carries an astronomical price tag. By using the ice and soil already present on Mars, we can literally print the colony into existence, moving from a prefabricated outpost to a truly self-expanding settlement. The first greenhouse grown from Martian water and soil would be more than a source of food. It would be a symbol of a new kind of architecture, one that is born from the land itself. This deep layer of frozen water does more than just build walls, it builds a stable environment. The Martian surface is a place of thermal extremes, where daytime temperatures can reach an almost pleasant level before plummeting by nearly 100 degrees Celsius after sunset. These swings are brutal, testing the limits of every machine and structure. Yet just a few meters down, the story changes completely. The subsurface ice acts as a colossal thermal battery, absorbing heat during the day and slowly releasing it throughout the long, frigid night. This is the principle of thermal mass, something we see in thick stone walls on Earth that keep buildings cool in summer and warm in winter. On Mars, the ice itself becomes that stabilizing stone. A habitat constructed directly into this icy regolith, or even just built above a significant deposit, would tap into this natural regulation. The interior temperature would not spike and crash with the sun, but would instead hover in a much narrower, far more manageable range. Think of the difference between a flimsy tent in the desert and a cabin built into the side of a mountain. One is at the mercy of the elements, while the other maintains its own quiet equilibrium. For a Martian colony, this passive climate control is a gift of immense value. The life support systems would not need to work as hard, burning far less precious energy on massive heaters during the night or powerful coolers during the day. This efficiency translates directly into resilience, making the entire outpost safer for its human inhabitants and kinder to its sensitive machinery. The ice, in its silent, frozen state, becomes an active partner in creating a livable world. Smoothing out the planet's most violent temperature swings into something that feels remarkably like home. Beyond the life support systems and the fuel depots, this local water source provides an even more fundamental resource: peace of mind. For the first colonists, the most profound danger may not be radiation or the thin air, but the deep-seated anxiety of living in a place where every single breath of air and sip of water is a finite resource shipped from a world millions of kilometers away. That relentless awareness of total dependence can weigh heavily on the human spirit, but the moment colonists can watch their own machines pull water from the ground and process it into a clear, drinkable stream, that psychology shifts entirely. The sight of water vapor condensing into a reservoir or the feel of moist soil in a greenhouse where food is growing transforms an abstract concept of survival into a tangible, daily reality. This is no longer just a remote outpost clinging to existence. It is a home that can provide for itself. The knowledge that a backup supply is not a year-long resupply mission away, but is literally right beneath their feet, builds a unique form of confidence. It fosters a resilient mindset, one focused on growth and the future rather than mere day-to-day endurance. This mental security, born from the certainty of water, is the invisible shield that protects the colony just as surely as any radiation wall, making the entire endeavor not just technologically possible, but humanly sustainable for generations to come. Far to the north and south of Mars lie its most dramatic reservoirs of water, the immense polar ice caps. These sprawling, brilliant white features are not just simple sheets of ice. They are complex, layered structures of water ice and frozen carbon dioxide, what we commonly call dry ice, that expand and contract with the Martian seasons. In the bitter cold of a polar winter, temperatures plummet so low that a significant portion of the planet's thin atmosphere freezes solid, settling as a layer of carbon dioxide frost that can be meters thick. When summer arrives, this frozen carbon dioxide does not melt into a liquid. Instead, it sublimates, transforming directly from a solid back into a gas and escapes into the atmosphere. This seasonal dance reveals the underlying layers of much more permanent water ice. These caps are a testament to the scale of water on Mars, holding a volume that, if completely melted, could cover the entire planet in an ocean. For scientists, they are a frozen climate record. Each layer of ice and dust laid down over millions of years holds clues about the planet's past, much like the ice cores drilled from glaciers here on Earth. By studying the composition and structure of the polar caps, researchers can piece together the history of Mars's shifting climate, its atmospheric changes, and the fate of its ancient water. Yet for all their scientific value, these polar regions are unlikely to be the first homes for human colonies. The conditions are simply too extreme. The winters are periods of perpetual darkness, and the temperatures are far colder than anywhere else on the planet. Their remote location, far from the sun-drenched, more temperate equatorial zones, also adds immense logistical complexity to any mission. So why study them so intently? They provide the essential context for the smaller, more accessible deposits we have been discussing. Understanding the grand, planetary scale of water at the poles helps us interpret the smaller-scale clues of subsurface ice in the mid-latitudes. It confirms that the water we are hunting for in those more hospitable regions is part of a much larger, global system. This bridge between pure planetary science and practical engineering is vital. The polar caps tell us the full story of water on Mars, while the subsurface ice deposits offer the first practical chapters we can actually write ourselves. But this frozen treasure is not a pristine, crystalline block. Martian ice is a complex chemical mixture forged in an alien environment. It is almost certainly laced with substances that make it utterly undrinkable and potentially hazardous in its raw form. The most significant of these are perchlorates, a type of salt that is widespread in the Martian soil. On Earth, perchlorates are used in things like rocket propellant and fireworks because they are powerful oxidizers. But for the human body, they are a serious problem. These compounds can interfere with thyroid function, disrupting the body's ability to regulate its own metabolism. Ingesting even small amounts over time could lead to significant health challenges for a colonist. This means the very resource meant to sustain life arrives with a built-in poison, a paradox that must be solved by technology. The presence of perchlorates, along with fine Martian dust and other salts, transforms the water extraction process. It is no longer just about melting and pumping. It becomes a multi-stage industrial purification effort, a chemical ballet that must be performed flawlessly to produce a safe, clear stream. The first step after extraction is often a coarse filtration to remove the larger particles of soil and dust. Then, to tackle the dissolved salts and perchlorates, the colony would likely use a process called reverse osmosis. Imagine forcing the contaminated water through a membrane with pores so incredibly tiny that only pure water molecules can squeeze through, leaving the larger contaminant molecules behind. It is like using an impossibly fine sieve to separate salt from water. Another method is simple distillation, a technique as old as civilization itself, but re-engineered for a new world. The dirty water would be boiled, and the resulting steam, which is pure water vapor, would be captured and cooled back into liquid, leaving the solid perchlorates and salts behind in the original chamber. For the most stubborn chemical contaminants, more advanced systems might employ specialized resins or catalysts designed to bind with perchlorate molecules and pull them out of the solution. This entire purification plant would be a critical, non-negotiable component of the colony's infrastructure, humming away constantly. Its success defines the thin line between a self-sustaining settlement and a doomed expedition. The chemistry of the ice, therefore, adds a profound layer of challenge. It reminds us that the abundance of water on Mars is not a simple answer, but a complex question. It demands not just the brute force of excavation, but the refined intelligence of chemical engineering, turning a hostile mixture into the clear, life-giving resource that will fuel a new chapter for humanity. A single well can support a handful of pioneers, but a city demands an aquifer. The transition from a lonely outpost to a bustling, self-perpetuating metropolis is a story written in water. It begins with the first successful ice mine, a single site producing a steady trickle of water for life support and fuel. But as more people arrive, that trickle must become a river. This is not merely a matter of digging more holes, it is about building an industrial ecosystem. A second and third extraction site would be established, each feeding into a central, vastly enlarged water processing plant. This facility would no longer be a single, experimental unit, but a sprawling industrial complex humming with activity. Its distillation columns and reverse osmosis membranes working around the clock to purify thousands of liters daily. The hydrogen and oxygen produced would no longer be stored in a few isolated tanks. Instead, a network of distributed fuel depots would emerge, acting like interstellar gas stations strategically placed near launch pads and major power grids. This distributed system creates resilience, a colony where a single point of failure cannot cripple the entire settlement. The architecture of safety would scale in tandem. New habitats would not be built in isolation, but connected, forming districts sheltered under interconnected, ice-shielded domes or carved into the frozen ground itself. This creates a positive feedback loop, the very engine of growth. More reliable water and power allow the colony to support more people. A larger population provides the skilled labor necessary to build the next extraction site, the next processing plant, and the next habitat cluster. Each new module makes the whole system more robust and capable, which in turn supports even more growth. This is how a foothold becomes a home, and then a homeland. It is a cycle where the initial resource, the subsurface ice, fuels its own expansion, transforming a fragile human presence into a civilization that is not just surviving on Mars, but is actively, permanently building its future there. This transformation of water into fuel, power, and shelter points toward an even greater revolution, an economic one. On Mars, water will not merely be a resource, it will become the fundamental currency of a new civilization. Every liter extracted from the ground carries a tangible value far exceeding its weight because it is the universal feedstock. It is the raw material for the air you breathe, the electricity that powers your tools, the fuel that launches your ships, and the very walls that keep you safe from radiation. This intrinsic utility makes it the natural backbone of a Martian economy. In such a system, the concept of a water credit becomes a logical unit of exchange. One credit could represent the energy potential locked inside a specific volume of purified water, a measure of the breathable air it can create, or the amount of radiation shielding it can provide. Barter and trade between different outposts or corporate entities could be conducted in these terms, a system built not on abstract numbers but on the direct, life-sustaining power of the colony's most vital asset. This establishes a truly self-contained economy, one that is independent of Earth's financial markets and grounded in the physical reality of survival and growth on a new world. This economic foundation then unlocks Mars's greatest strategic value for all of humanity. The planet's position becomes its prime commodity. Think of the immense energy and cost required to launch a spacecraft out of Earth's deep gravity well, fighting against the planet's powerful pull with every kilogram of fuel. Now imagine a ship designed to travel to the asteroid belt or beyond. It launches from Earth with only the fuel needed to reach Mars, arriving with its tanks nearly empty. There it docks at an orbital station or a surface depot and refuels with propellant manufactured from Martian water. This single innovation completely rewrites the economics of deep space travel. Mars, with its lower gravity and ready-made fuel factories, becomes the most strategic pit stop in the inner solar system. It transforms from a distant destination into a central hub, a bustling interplanetary port where ships bound for the riches of the asteroid belt or the mysteries of the outer planets stop to fill their tanks. The water mined from its soil becomes the gasoline that powers the next great age of exploration, turning the red planet into the gas station for the entire solar system. This economic engine does not have to stop at the planet's edge. The very resources that make a Martian colony self-sufficient could also become its most valuable exports, transforming the planet from a remote outpost into a central hub of interplanetary commerce. While it would never make economic sense to ship jugs of water back to Earth, the high-value products derived from that water are a different story. Think of the immense energy required to manufacture certain materials, like ultra-pure silicon for computer chips or specialized alloys for spacecraft. Mars, with its vast, undeveloped landscape, could host massive solar farms or next-generation nuclear reactors, generating power on a scale that is difficult to achieve on our crowded planet. This cheap, abundant energy, combined with a limitless supply of water for both processing and cooling, could position Mars as a manufacturing powerhouse for the entire inner solar system. It would ship not raw ore but finished, high-precision components, using its two most abundant resources, sunlight and water, to create goods that are too energy-intensive to produce economically on Earth. This vision elevates Mars from a colony to an industrial partner, but the first and most immediate customers would be much closer to home. The small, potato-shaped moons of Mars, Phobos and Deimos, are potential way stations themselves. Any sustained activity there would need the same life-giving resources. A small research station on Phobos would be a perfect client for a Martian enterprise, purchasing shipments of purified water, breathable air, and prefabricated rocket fuel, all launched from the Martian surface at a fraction of the energy cost required to lift them from Earth. This creates a local inter-moon economy with Mars as the central supplier. This flow of trade does more than just generate revenue, it forges a network of interdependence. By supplying other space-based ventures, Mars secures its own economic and political independence. It builds alliances and creates a self-sustaining economic sphere that is not reliant on subsidies or shipments from its home world. The water mined from its soil becomes the foundation of its sovereignty, the liquid asset that fuels not just its own survival, but its rise as a pivotal, independent world in the solar system's future. Yet this grand vision of a Martian civilization raises a profound and deeply human question, one that goes far beyond engineering. As we prepare to extract water and reshape the landscape, we must confront the ethics of our actions on a planet that is not our own. This debate centers on the principle of planetary protection, a long-standing guideline designed to prevent biological contamination between worlds. On one side of this discussion are those who advocate for preserving Mars in its most pristine state. They argue that the planet is a unique scientific laboratory, a record of potential ancient life and planetary evolution that could be irrevocably lost if we introduce Earth-based microbes or drastically alter the environment. For them, Mars holds answers to fundamental questions about life in the universe, and our first priority should be to study it, not change it. The opposing view champions a more utilitarian approach, often framed as a form of interplanetary free market. Proponents argue that the survival and expansion of humanity is the highest ethical calling, and that the resources of the solar system are there to be used responsibly to ensure our species' long-term future. They see the subsurface ice not as a museum piece, but as the key to that future. This is not a simple disagreement, it is a fundamental conflict of values. It forces us to ask, do we have the right to significantly alter another world? And if we do, what responsibilities come with that power? The most critical responsibility involves the search for native life. If Martian microbes exist, likely sheltered in deep aquifers or within the icy soil itself, our industrial activity could pose an existential threat. Our drilling operations could introduce hardy Earth bacteria that outcompete and eradicate these native organisms before we ever have a chance to discover them. To prevent this, any mining operation would need to be preceded by rigorous biological surveys and potentially operate under strict sterilization protocols, treating the worksite with the same care as a surgical theater. This adds immense complexity and cost, but it acknowledges a monumental duty. We are not just visitors to Mars, we are the first representatives of a biosphere arriving at another. The choices we make now about how we use this water and shape this world will set a precedent for all the worlds that may follow. They will define what kind of interstellar citizens we truly are. These robotic pioneers will operate in a profound silence, their only audience the twin moons in the sky. Before the first human footstep is planted, these machines must perform a symphony of complex tasks entirely on their own. They are not merely remote-controlled toys. Their commands sent from Earth would take too long to arrive, making real-time control an impossibility. Instead, they must possess a form of artificial cognition, an ability to perceive their environment, make critical decisions, and execute intricate procedures without a single word from home. Picture a fleet of robotic vehicles that look nothing like the rovers we know today. They are larger, heavier, and built for pure industrial purpose. Their primary job is to transform a designated patch of Martian desert into a functioning mine. One machine, a mobile drill rig, would navigate to a precise coordinate mapped from orbit. It would then need to stabilize itself on the uneven, rocky ground, deploying outriggers to create a level platform. Its drill, a sophisticated piece of engineering, must then bite into the frozen soil, adjusting its torque and speed in real time based on the hardness of the material it encounters. Is it hitting a patch of pure ice or a stubborn layer of cemented rock? The AI must interpret the sensor data from the drill bit and adapt its strategy on the fly, all while managing its own power consumption and monitoring its mechanical health. This is the difference between a simple machine and a smart foreman. It does not just follow a list of commands, it executes a mission with a goal, navigating 1,000 small uncertainties to achieve it. Alongside the drill, other robotic units would be focused on excavation. These are the autonomous diggers and haulers, the construction crew of the New World. Their challenge is the terrain itself. The surface of Mars is littered with dust, sand, and rocks of every size, a landscape that can shift without warning. A path that was clear one Sol or Martian day might be blocked by a newly revealed boulder the next. The AI guiding these machines is their eyes and their instinct. It fuses data from stereo cameras, laser rangefinders, and inertial sensors to build a constantly updating three-dimensional map of its surroundings. It must identify stable ground, calculate the safest route to the processing plant, and avoid any obstacle, all while carrying a heavy load of icy regolith. This is not a pre-programmed path. It is a dynamic dance with an unpredictable environment. The system must be capable of recognizing when it is stuck and knowing the series of maneuvers to free itself. It is a level of spatial reasoning and problem-solving that pushes the boundaries of machine intelligence. But perhaps the most critical ability these systems will need is self-preservation. A breakdown millions of kilometers from the nearest workshop is a mission-ending event. Therefore, the robotic miners must be their own diagnosticians and mechanics. Their AI will continuously monitor the status of every critical component, from motor temperatures to joint actuators. If a part shows signs of abnormal wear, the system must be able to identify the issue, determine if it can be fixed autonomously, and if so, execute the repair. This might involve a companion robot, a dedicated maintenance unit, being dispatched to the site. This smaller machine could use specialized tools to replace a faulty motor or clear dust from a clogged filter. This is not a futuristic fantasy. It is a necessary evolution of technology we see today in automated factories, just transplanted to the most demanding workshop imaginable. This partnership between human foresight and machine execution is the only way to build the foundation for a colony. The robots do not just extract ice, they build trust. They prove that the life-giving resources are waiting, that the machinery works, and that the environment, while harsh, can be mastered. They are the silent, steadfast workforce that turns a map of potential into a stockpile of reality, preparing a home for the people who will one day follow. The true power of Martian water is revealed only when it connects with the planet's other abundant resources. This is not a single solution, but a symphony of chemistry and engineering where each element amplifies the others. The thin Martian atmosphere, composed almost entirely of carbon dioxide, might seem like a void, but to a chemical engineer, it is a reservoir of potential. Combine this atmospheric carbon dioxide with the hydrogen gas split from water ice, and you unlock a reaction that is foundational for a true Martian economy. This process happens inside a device called a Sabatier reactor. Inside its heated chambers, carbon dioxide and hydrogen are brought together over a special catalyst, triggering a chemical marriage. The output is methane, a powerful and stable rocket fuel, and more water. This is a beautifully closed loop. You start with water and air, and you end up with rocket fuel and even more water to feed back into the cycle. This single reaction solves one of the biggest hurdles for a self-sustaining colony, producing a high-performance fuel like methane that is easier to store for long periods than liquid hydrogen. The water you mine does not just become fuel once, it becomes the seed for a perpetual fuel factory, working in harmony with the atmosphere itself. This synergy extends to the very ground beneath your feet. The red Martian soil, or regolith, is more than just dirt. It is a versatile building material and a ready-made shield. When you excavate ice, you are also moving vast quantities of this regolith. Instead of treating it as waste, it becomes a primary asset. Bulk regolith can be piled onto habitats or packed into walls, providing excellent protection against cosmic radiation. Its granular nature also makes it a superb insulator, buffering the habitat against the planet's extreme temperature swings, but its use does not stop at simple shielding. With the right technology, this soil can be processed into bricks, ceramics, or even concrete, using the water you have mined as a key ingredient. Imagine a 3D printer constructing a habitat wall layer by layer, not with plastic, but with a paste of Martian soil and water, fused solid by the freezing air. This creates a powerful, three-legged foundation for survival. The water provides life support and fuel, the atmosphere is transformed into more fuel and water, and the regolith provides the physical structure and protection for it all. Each resource makes the others more valuable, weaving a safety net so strong that the colony is no longer dependent on any single shipment from Earth. This is the essence of true sustainability, building a world not from imported parts, but from the very fabric of the planet itself. But can a civilization truly build its future on a resource that might simply vanish over time? The long-term stability of this subsurface ice is not just an academic question, it is the bedrock of any permanent settlement. While the surface of Mars is a dry and windswept desert, the ice hidden below is remarkably well preserved, locked in a state of deep freeze for millions of years. The key to its stability lies in the combination of depth and pressure. At a certain depth beneath the surface, the weight of the overlying soil and rock creates enough pressure to prevent the ice from sublimating, from turning directly from a solid into a vapor in the thin Martian air. This creates a stable layer, a geological refrigerator where the ice remains safely trapped. Furthermore, the mid-latitude regions where we would likely build are in a thermal sweet spot, far enough from the equator to avoid excessive warming, yet not so far toward the poles that they are locked in perpetual, deep cold. This balance suggests that these particular deposits are not a fleeting phenomenon, but a permanent feature of the Martian landscape, a reliable reservoir that has endured through immense stretches of planetary history. However, Mars is not a dead world in a geological sense. It experiences subtle seismic shifts, masquaks that gently rattle the ground. While these are not the planet-shattering events we see on Earth, they are a reminder that the subsurface is dynamic. A significant tremor could theoretically fracture an icy layer, creating new pathways to the surface and allowing a deposit to slowly bleed its water vapor into the atmosphere over centuries. This is not a reason for alarm, but a call for vigilance. A mature colony would not simply assume the ice is forever. It would weave planetary monitoring directly into its infrastructure, using networks of seismometers to listen to the heartbeat of the planet and sensors to track the integrity of its water vaults. This transforms resource management from a static plan into a dynamic conversation with the planet itself. The strategy is not to find a static resource and exploit it until it is gone, but to build a society that can listen, learn, and adapt, ensuring that the frozen treasure beneath its feet remains secure for all the generations to come. This frozen water is far more than a simple utility. It is a sealed library holding the untold story of Mars. Each layer of ice, built up over countless millennia, is a page in a climate record waiting to be read. The very act of mining this ice can become a profound scientific mission, one that runs in parallel with the colony's industrial work. As drills bite into the icy ground to extract water for fuel and air, they will simultaneously be retrieving pristine ice cores, long cylindrical samples that preserve a timeline of environmental change. Scientists on Earth perform this same kind of detective work with ice cores from Greenland and Antarctica, but the Martian cores would be revolutionary. They would contain fine layers of ancient Martian dust deposited by long-forgotten dust storms, and most importantly, microscopic bubbles of the planet's ancient atmosphere trapped as the ice formed. Analyzing the composition of these gases, the ratios of different isotopes, and the chemistry of the dust would allow researchers to reconstruct the Martian climate year by year for millions of years into the past. We could finally answer fundamental questions with hard data. Was Mars ever truly warm and wet for long periods? How did its thick atmosphere dissipate into the thin veil we see today? Did the conditions for life ever persist on the surface long enough for it to take hold? This transforms the colony's purpose, elevating it from a struggle for survival into a beacon of discovery. The same industrial site producing rocket fuel would also be the source of humanity's deepest understanding of our planetary neighbor. The colonists would not just be engineers and farmers, they would be archivists, unsealing a historical record that has been locked away for eons, forever changing our place in the cosmic story. Even the most carefully mapped ice deposit could one day run dry or face an unexpected challenge. This reality is why a truly resilient colony will be built not on a single well, but on a network of them. The first and most fundamental layer of protection is geographical diversity. Rather than concentrating all extraction efforts in one location, multiple, widely separated mining sites would be established, each tapping into its own independent reservoir. Think of it like a city that draws its water from several different watersheds. If one source becomes compromised, the others can temporarily increase their output to support the population. This distributed approach ensures that a single point of failure, perhaps a localized geological shift or a technical issue at one mine, cannot jeopardize the entire settlement. This strategy transforms the colony's resource base from a single, fragile thread into a robust, interwoven web. Alongside this geographical redundancy, the colony's internal systems must be masters of conservation. The very air you breathe and the water you drink would be part of a meticulously managed, closed-loop cycle. Advanced systems would constantly scrub carbon dioxide from the habitat air, not just to keep it breathable, but to capture the carbon atoms for other uses. Every drop of moisture, from the humidity in the air to the water in waste, would be captured, purified, and reintroduced into the system. This is not merely recycling, it is hyper-efficiency, a relentless effort to minimize any loss and squeeze every possible molecule of value from the resources already in circulation. These two systems, the external network of mines and the internal loops of recycling, create a powerful synergy, but even the most self-sufficient system benefits from a final, ultimate safeguard. Maintaining a contingency for emergency resupply from Earth, however costly and infrequently used, acts as a profound psychological and practical safety net. It is the acknowledgement that for all our planning, we are still pioneers in a profoundly alien environment. This multi-layered approach to risk, blending redundancy, efficiency, and a fallback option, demonstrates that the vision for Mars is not a reckless gamble. It is a carefully considered, deeply responsible blueprint for permanence, where the ability to adapt and endure is engineered directly into the foundation of the new world. The first light of the Martian sun filters softly through the thick, translucent ceiling of ice. Inside the habitat, the air is warm and carries the faint, earthy scent of the aeroponics bay. A colonist begins their day not with the rumble of a city, but with the quiet hum of machinery and life support. The water for their morning coffee flows from a tap, clear and cold, having been purified just hours before from the subsurface reservoir directly beneath their feet. This simple, daily ritual is a quiet miracle, a testament to the colony's fragile but growing independence. After a breakfast that includes greens from the greenhouse, their work shift begins. The walk to the greenhouse module is short, through a connecting tunnel whose walls are lined with packed regolith, but stepping inside is always a shock of vibrant green. The walls here are made of clear ice panels, bathing the rows of lettuce, tomatoes, and tubers in a diffused, gentle light. The air is humid and rich with the smell of growth. As they check the nutrient misters, the water cycling through the system is the same water that was mined from the ground, a constant loop of life that turns frozen treasure into fresh food. The heart of the colony's industry, however, lies in the electrolysis plant. The transition from the organic warmth of the greenhouse to the clean, ordered space of the fuel factory is stark. Here, the low, powerful thrum of compressors fills the air. Their task is to monitor the consoles that oversee the splitting of water into its elemental parts. On one screen, a clear stream of purified water enters the electrolysis chamber. On another, two separate gauges track the steady production of gaseous oxygen and hydrogen. The oxygen is diverted to replenish the habitat's central atmosphere, while the hydrogen is chilled and condensed into a pale, supercold liquid destined for the fuel depot. This daily production is not an abstract process. It is the literal creation of the colony's breath and its bridge back to Earth, all flowing from the steady, reliable pulse of water pulled from the Martian ground. This is a world where the most advanced technology has a single, humble purpose: to transform the ancient ice of a dead planet into the rhythm of a new life. This grand undertaking will require more than the ambition of a single nation. It demands a global alliance. The sheer scale and cost of establishing a functioning ice mining colony on Mars makes international partnership not just beneficial but essential. Picture a mission where NASA, a deep space navigation and landing expertise, guides the spacecraft, while the European Space Agency provides the life support and closed-loop recycling systems. Roscosmos could contribute its decades of experience in long-duration space habitation, and the China National Space Administration might deploy advanced robotic rovers for surface operations. Alongside these national agencies, private companies like SpaceX would inject their signature innovation and drive for cost efficiency, perhaps specializing in the heavy lift launch vehicles and the design of the surface habitats themselves. This is not a competition, but a convergence where each partner brings a unique piece of the puzzle. One nation might perfect the deep drilling technology needed to access the ice, while another develops the compact nuclear reactors required to power the entire operation. A third might specialize in the sophisticated chemical plants that purify the water and synthesize rocket fuel. This division of labor spreads the immense financial burden and, more importantly, pools the collective intelligence of our entire species. The common goal of utilizing Martian ice becomes a powerful catalyst, forging bonds of shared purpose and technical interdependence that transcend terrestrial politics. In this shared endeavor, the Red Planet becomes a neutral workshop, a project that unites humanity in the common cause of ensuring its long-term survival among the stars. This collaboration could forge a new model of global cooperation, proving that our greatest challenges are best met not in isolation, but together. The mastery of Martian ice would mark a threshold in human history, a moment where our civilization truly becomes multiplanetary. For the first time, we would not just be visitors camping on another world, but residents who have learned to live off its land. This breaks an ancient chain of dependency, the idea that humanity can only thrive on the single, fragile planet of its origin. Think of it as a new chapter in our story, one as profound as the shift from hunting and gathering to settled agriculture. That earlier revolution allowed us to build cities and cultures, planting our roots deep into the soil of Earth. The Martian water revolution would do the same, but on an interplanetary scale, planting our roots in the rust-colored soil of a new world. The knowledge gained, the technologies perfected, and the hard-won wisdom of creating a self-sustaining biosphere from scratch would become our most valuable inheritance. This is not merely about survival, it is about the birth of a new branch of human civilization. The lessons written in the ice and the regolith would form the foundational textbook for life beyond Earth, a guide for settling the moons of the outer solar system and one day journeying to the stars. Every step taken to extract that water, to build with it, and to power a colony with it secures more than just the future of a single outpost. It ensures the long-term survival and diversification of our entire species, turning humanity from a single-world phenomenon into an enduring presence across the cosmos. This journey from hidden ice to a humming metropolis reveals a simple, profound truth. The story of settling Mars is at its heart a story of water. That frozen layer beneath the dust is so much more than a scientific curiosity. It is the absolute cornerstone of the entire endeavor. It is the fuel for our rockets, the air in our lungs, the shield on our walls, and the very currency of a new economy. This single resource weaves together every thread of survival and ambition, transforming a distant dream into a tangible, achievable future. The path forward is undeniably steep, filled with immense engineering puzzles and complex ethical questions we are only beginning to navigate. Yet the reward waiting on the other side of that challenge is beyond any simple measure. It is the birth of a self-sustaining civilization, the opening of a new chapter in the human story, and a crucial safeguard for the long-term future of our species. The silent, frozen treasure is already there, waiting under the rust-colored sands. The choice to reach for it, to turn this vision into reality, now rests squarely in our hands. If this future calls to you, subscribe to join our ongoing exploration of the technologies and ideas that will build our destiny among the stars.